Welcome to our deep dive into the fascinating world of atomic orbitals. Today, we'll unravel the mysteries behind the shapes and behaviors of electrons as they surround the nucleus of an atom. Understanding atomic orbitals is key to grasping how atoms bond, interact, and form the very matter that makes up our universe. Let's embark on this journey by first exploring what an atomic orbital actually is, and why it's so fundamental to chemistry and physics. Get ready to see atoms in a whole new light as we begin our exploration. Atomic orbital is not a physical path or orbit, but rather a region in space where there is a high probability of finding an electron. Unlike the orbits in the solar system, electrons and atoms exist in these fuzzy, cloud-like regions. These orbitals are defined by quantum mechanics and are described by mathematical functions known as wave functions. The concept of orbitals helps us visualize where electrons are likely to be found around the nucleus, which is crucial for understanding chemical bonding and the properties of elements. Quantum mechanical model of the atom replaced earlier models that pictured electrons orbiting the nucleus like planets around the sun. Instead, quantum mechanics tells us that electrons behave both like particles and waves. This dual nature means we can't pinpoint their exact location, but we can predict the probability of finding them in certain regions. These are the atomic orbitals. This model is more accurate and explains many properties of atoms that earlier models could not. The heart of atomic orbitals is Schrödinger's equation, a fundamental equation in quantum mechanics. This mathematical formula allows scientists to calculate the wave functions of electrons in atoms. The solutions to this equation give us the shapes and energies of the orbitals. It's a complex topic, but the key takeaway is that Schrödinger's equation helps us understand where electrons are most likely to be found, which is essential for predicting chemical behavior. Principal quantum number, symbolized as n, is one of the key numbers that describe atomic orbitals. It indicates the main energy level or shell in which an electron resides. The higher the value of n, the farther the electron is from the nucleus and the higher its energy. This quantum number helps organize electrons into different shells, which is crucial for understanding the structure of the periodic table and the behavior of elements. Another important quantum number is the angular momentum quantum number, represented by L. This number determines the shape of the orbital. For each value of n, L can range from 0 up to n1. Each value of L corresponds to a different type of orbital, sp, d, or these shapes play a significant role in how atoms bond and interact with each other, influencing the chemistry of the elements. Magnetic quantum number, denoted as ml, specifies the orientation of the orbital in space. For each value of L, ml can take on integer values from L to plus L. This quantum number becomes especially important when atoms are placed in a magnetic field, as it helps determine how the orbitals align. Understanding ml is key to predicting the behavior of electrons in different environments. Spin quantum number, symbolized as ms, describes the intrinsic spin of the electron. Electrons can have a spin of +1,2 or -1,2. This property is fundamental to the Pauli exclusion principle, which states that no two electrons in the same atom can have the same set of quantum numbers. The concept of spin is crucial for understanding the arrangement of electrons and the magnetic properties of atoms. Let's start with the simplest type of orbital, the s orbital. S orbitals are spherical in shape and can be found in every energy level. The one's orbital is closest to the nucleus, while higher s orbitals like 2s, 3s are larger and farther out. Because of their symmetry, s orbitals play a foundational role in the structure of atoms and the way electrons fill up energy levels. Next, we have the p orbitals, which start appearing at the second energy level, n equals 2. These orbitals have a distinctive dumbbell shape and are oriented along the x, y, and z axes. There are 3 p orbitals in each energy level where they exist, and they play a major role in forming covalent bonds. The unique shape and orientation of p orbitals allow for the creation of complex molecules. Moving up in complexity, d orbitals appear starting at the third energy level, n equals 3. There are 5 d orbitals in each shell where they exist, and their shapes are more complex, often resembling cloverleaves or other intricate forms. These orbitals are essential for understanding the chemistry of transition metals and the formation of colorful compounds. The f orbitals are even more intricate, with 7 unique shapes in each shell where they appear, starting at the fourth energy level, n equals 4. These orbitals are important for the chemistry of the lanthanides and actinides, elements found at the bottom of the periodic table. The complexity of f orbitals contributes to the unique properties of these rare elements. Visualizing atomic orbitals can be challenging, but scientists use computer models and mathematical plots to represent their shapes. These visualizations help us understand how electrons are distributed around the nucleus and how they influence chemical bonding. By studying these shapes, we gain insight into the behavior of atoms and molecules in the real world. The concept of electron probability density is central to atomic orbitals. Instead of knowing exactly where an electron is, we talk about the probability of finding it in a certain region. This probability is highest near the nucleus and decreases as you move farther away. The shapes of orbitals are essentially maps of these probabilities, showing where electrons are most likely to be found. Nodes are regions within an orbital where the probability of finding an electron is 0. There are 2 types of nodes: radial nodes, which are spherical, and angular nodes, which are planar. The number and type of nodes depend on the quantum numbers of the orbital. Understanding nodes helps explain the energy differences between orbitals and why electrons fill them in a specific order. Atomic orbitals are organized into energy levels and sublevels. Each principal energy level contains one or more sublevels, which are made up of different types of orbitals, s, p, d, f. The arrangement of these sublevels determines how electrons fill up an atom, following specific rules that we'll explore in the next scenes. Aufbau Principle states that electrons fill the lowest energy orbitals first before moving to higher ones. This rule helps explain the order in which electrons populate the various orbitals in an atom. By following the Aufbau Principle, we can predict the electron configuration of any element, which is essential for understanding its chemical properties. Pauli exclusion principle is a fundamental rule in quantum mechanics. It states that no two electrons in the same atom can have the same set of 4 quantum numbers. This means that each orbital can hold a maximum of 2 electrons, and they must have opposite spins. This principle is crucial for understanding the structure of the periodic table and the behavior of electrons in atoms. Hund's rule states that electrons will fill degenerate orbitals with the same energy singly before pairing up. This minimizes electron repulsion and stabilizes the atom. Hund's rule helps explain the arrangement of electrons in p, d, and f orbitals and is key to understanding the magnetic properties of atoms. Electron configuration notation is a shorthand way of showing how electrons are distributed among the orbitals of an atom. For example, the configuration for hydrogen is 1s1, while for oxygen it's 1s22s22p. For this notation helps chemists quickly understand the structure and reactivity of elements. Structure of the periodic table is closely linked to the arrangement of atomic orbitals. Elements in the same group have similar electron configurations, which gives them similar chemical properties. The periodic table is divided into blocks S, P, D, F based on the type of orbital being filled. This organization helps us predict the behavior of elements. Valence electrons are the electrons in the outermost shell of an atom. These electrons are the most important for chemical bonding, as they are the ones involved in forming bonds with other atoms. The number of valence electrons determines an element's reactivity and the types of bonds it can form. Core electrons are the electrons found in the inner shells of an atom, closer to the nucleus. Unlike valence electrons, core electrons are not usually involved in chemical bonding. However, they play a role in shielding the valence electrons from the full charge of the nucleus, affecting the atom's properties. Orbital hybridization is a concept that explains how atomic orbitals mix to form new hybrid orbitals during chemical bonding. For example, in methane CH4, the carbon atoms s and p orbitals combine to form 4 equivalent sp3 hybrid orbitals. This concept is essential for understanding the shapes of molecules and the types of bonds they form. Sigma, and pi bonds are 2 types of covalent bonds formed by the overlap of atomic orbitals. Sigma bonds are formed by the head-on overlap of orbitals, while pi bonds result from the side-by-side overlap. Understanding these bonds is crucial for predicting the structure and reactivity of molecules. When atoms bond to form molecules, their atomic orbitals combine to create molecular orbitals. These new orbitals can be bonding or antibonding, and their arrangement determines the stability and properties of the molecule. Molecular orbital theory provides a more detailed understanding of chemical bonding than the simple Lewis structure approach. Bonding orbitals are lower in energy and help hold atoms together, while antibonding orbitals are higher in energy and can weaken or prevent bonding. The way electrons fill these orbitals determines whether a molecule is stable or not. This concept is key to understanding why some molecules form and others do not. The electron cloud model is a way of visualizing where electrons are likely to be found around the nucleus. Instead of fixed paths, electrons exist in a cloud of probability. This model reflects the uncertainty and complexity of quantum mechanics, giving us a more accurate picture of atomic structure. The Heisenberg uncertainty principle states that it's impossible to know both the exact position and momentum of an electron at the same time. This principle is fundamental to quantum mechanics and explains why we talk about probabilities and clouds when describing atomic orbitals. Let's quickly recap the 4 quantum numbers: principal N, angular momentum L, magnetic ML, and spin MS. Together, these numbers uniquely identify each electron in an atom and determine the structure of atomic orbitals. Mastering these concepts is essential for anyone studying chemistry or physics. Spectroscopy is a technique used to study the energy levels of electrons in atoms. When electrons move between orbitals, they absorb or emit light at specific wavelengths. By analyzing this light, scientists can learn about the structure of atoms and the arrangement of their electrons. Photoelectric effect is a phenomenon where electrons are ejected from a material when it absorbs light. This effect provided key evidence for the quantum nature of electrons and the existence of discrete energy levels in atoms. It's a classic experiment that helped shape our understanding of atomic orbitals. When atoms are excited, their electrons jump to higher energy orbitals. As they return to lower energy states, they emit light at specific wavelengths, creating an emission spectrum. Each element has a unique spectrum which acts like a fingerprint for identifying it. This phenomenon is direct evidence of quantized energy levels in atoms. Understanding atomic orbitals is essential for many areas of chemistry. From predicting how elements will react to designing new materials and drugs, the concepts of orbitals and electron configuration are at the heart of modern science. Chemists use this knowledge to manipulate atoms and molecules for countless applications. In physics, atomic orbitals are crucial for understanding the behavior of matter at the smallest scales. They help explain phenomena like magnetism, conductivity, and the properties of solids and gases. The study of orbitals bridges the gap between classical and quantum physics, opening up new frontiers in technology and research. The arrangement of electrons in atomic orbitals determines whether an atom is magnetic. Unpaired electrons in orbitals can create magnetic moments, leading to phenomena like ferromagnetism and paramagnetism. Understanding this connection is important for developing new materials and technologies. Atomic orbitals are the foundation of chemical bonding. The way orbitals overlap and combine determines the strength, length, and type of bonds formed between atoms. This knowledge is essential for understanding everything from simple molecules like water to complex biomolecules like DNA. In organic chemistry, the concept of hybridized orbitals is used to explain the shapes and reactivity of carbon-based molecules. For example, the tetrahedral shape of methane is due to sp3 hybridization. Understanding orbitals helps chemists design new drugs and materials with specific properties. In inorganic chemistry, d and f orbitals play a major role in the behavior of transition metals and rare earth elements. These orbitals are responsible for the vibrant colors of many compounds and the unique magnetic and catalytic properties of these elements. Materials scientists use the concept of atomic orbitals to design new materials with specific electronic, magnetic, and optical properties. By manipulating the arrangement of electrons, they can create everything from superconductors to solar cells, revolutionizing technology and industry. Nanotechnology relies on a deep understanding of atomic orbitals to manipulate matter at the nanoscale. By controlling the arrangement of atoms and electrons, scientists can build new materials and devices with unprecedented precision and functionality. Quantum computing is an emerging field that harnesses the principles of quantum mechanics, including atomic orbitals, to process information in new ways. Understanding how electrons behave in orbitals is key to developing quantum bits or qubits, which are the building blocks of quantum computers. The study of atomic orbitals continues to drive innovation in science and technology. From new materials to advanced computing, the principles of quantum mechanics and atomic structure are shaping the future. As we learn more, we unlock new possibilities for discovery and invention. Let's summarize what we've learned. Atomic orbitals are regions where electrons are likely to be found, defined by quantum numbers and shaped by wave functions. They determine the structure and properties of atoms, influence chemical bonding, and are central to many scientific fields. Mastering these concepts opens the door to understanding the microscopic world. Thank you for joining us on this journey through atomic orbitals. We've explored the quantum world, learned about the shapes and behaviors of electrons, and seen how these concepts impact science and technology. Keep exploring and you'll discover even more about the incredible world of atoms and molecules.